Hello guys, we want to start our second lecture of chapter 13. So we want to talk about the solution of partial differential equation, and then we want to talk about superposition principle. So for solution of partial differential equations, we have different techniques to solve this kind of equation, but there is no general solution for partial differential equation. So you have to see which technique works for your PDE. But you have to keep in mind that we just focus in this lecture, we just focus on finding particular solution of PDE. We don't talk about the homogeneous solution of PDE. Then you have to know that we only employ separation of variables. So in fact, separation of variables is a technique for solving partial differential equation. So in this case, if you have one function like u, which is function of x and y, we use separation of variables. So it means that we assume that u of x and y is equal to x, which is a function of x, times y capital, which is a function of y. And then we solve our problem. It's separation of variable. And third, you have to know that this technique is not applicable for all the PDEs. I already said that there is no general solution for all the PDEs. This solution works just for some of the partial differential equation. For example, if you have one PDE like second derivative of u with respect to x plus derivative of u with respect to y equal to, let's say, x. So you cannot use separation of variable to solve this equation. So you have to find another solution for solving this PDE. So let's solve one example to see how we can use separation of variables to solve one partial differential equation. So in this equation, you want to solve in this example, you want to solve second derivative of u with respect to x plus second derivative of u with respect to y is equal to 0. In order to solve this problem, as I already said, you want to use separation of variables. So we assume that u of x and y is equal to a function of x times a function of y. So first, I have to find second derivative of u with respect to x in terms of x capital and y capital. With respect to x. Second derivative of u with respect to x, in fact, it's second derivative of x function times y function with respect to x. So we know that y capital is a function of y. As a result, when you want to take derivative with respect to x, it plays like a constant. You can take it out. So as a result, you have second derivative of x with respect to x. So it means that it's equal to y times x double prime. Now we have to find second derivative of u with respect to y. Again, so in this case, x is like a constant, so we have x times y double prime. Now I just plug it in the equation. In fact, we have x double prime times y capital plus x y double prime. It's equal to 0. So I can write this equation in this form. So x double prime divided by x, it's equal to minus y double prime divided by y. Now we have two functions, x double prime over x, which is function of x, and we have a function of y double prime over y, which is a function of y. In fact, we have two functions. They are equal, but they are functions of two different variables. The left hand side is a function of x, in right hand side is a function of y. So we have to see under what condition two functions with different variables they are equal. So just say note. Imagine I have two functions like this. So I have 2x divided by 2x plus 1 and 2y divided by 2y plus 1. When you see these two functions, so at first you may say that, okay, so these two functions are equal. But in fact, they are not equal. Why? Because if two functions are equal, they have to be equal for any values of x and y. Imagine x is equal to 0 and y is equal to 1. So we have x equal to 0. 2 times x, it's 0 divided by 1, so it's going to be 0. And the right hand side, we have 2 times y is 2 divided by 3. So we have 2 divided by 3. So you can see that these two functions are not equal. So now I give it another function. So imagine this function. Let me write it here. Imagine I have 4x plus 2 divided by 2x plus 1. And here we have 4y plus 2 divided by 2y plus 1. These two functions are equal. Why? Because if you pick any x and y, they are equal. For example, let's say we say x is equal to 0 and y is equal to 1. So if x is equal to 0, we have 4 times 0 plus 2 is 2. 2 times 0 plus 1 is 1, so it's 2. And if y is equal to 1, so we have 4y plus 2 is going to be equal to 6, divided 2y plus 1 is 3. So again, it's equal to 2. So you can see that these two functions are equal for any pair of x and y. But why they are equal? Because you know, in this case, numerator is a multiple of the denominator. If I just factor 2 here, so I have 2x plus 1. And here we have 2x plus 1. So they cancel. What is left? It's 2. The same here. If I just factor 2 here, so we have 2y plus 1 divided by 2y plus 1. Cancel. So we have equal to 2. So in fact, if we have two functions of different variables and they are equal, the only condition that they can be equal is that they should be constant. So here you can see that they are equal to 2. So it means that if here we have x double prime over x is equal to minus y double prime over y, so the only condition that they can be equal so is that these two functions should be constant. So I call it minus lambda. Why minus? It's just for the sake of simplicity. So you can consider it as plus lambda. So far we could find that x double prime divided by x, it's equal to minus lambda. As a result, x double prime plus lambda x is equal to 0. And y double prime divided by y, it's equal to, minus y double prime divided by y is minus lambda. As a result, y double prime minus lambda y is equal to 0. Now we have to find x and y. So the interesting point in using separation of variable is that now instead of solving partial differential equation, we have to solve two ordinary differential equation. The first one is x double prime plus lambda x is equal to 0. It's one ODE. And the second one is y double prime minus y lambda equal to 0 is another ODE. In order to solve these two equations, we have to consider different values for lambda. So in fact, we have to investigate what the solution is if lambda is 0, if it's a negative number, or if it's a positive number. So at first, I start with the first assumption. So I assume that 1, so lambda is equal to 0. If lambda is equal to 0, so it means that x double prime is equal to 0. If x double prime is equal to 0, it means that x prime of x should be a constant like a. And if x prime is a constant, so it means that x of x should be equal to a linear function, so ax plus b. So for the y, we have y double prime, it's equal to 0. As a result, y prime of y is equal to one constant. I call it c, for example. As a result, y of y is a linear function, so it's c y plus another constant, which is d. So we could find x and y. As a result, u of x and y, which is equal to x of x times y of y, it's equal to ax plus b times cy plus d. So we could solve this problem. We could solve this partial differential equation if we assume that lambda is equal to 0. Now I want to solve it if lambda is a positive number. So lambda, so in fact, is the second part of solution. So I assume that lambda is positive. So in order to have lambda positive, so I assume that it's equal to alpha squared, because alpha squared is always a positive number. So if I plug a positive alpha squared into PDE that we have, so we have x double prime plus alpha squared x is equal to 0. As a result, so if you solve this ordinary differential equation, you already have it in the formula sheet. So x of x, it's equal to another constant. So you say a cosine alpha x plus b sine alpha x. A and b, they are two arbitrary constants, but this a and b is different from what we found when lambda is equal to 0. And for the second equation, so we have y double prime minus alpha squared y, it's equal to 0. As a result, y of y, it's equal to c cosine hyperbolic alpha y plus d sine hyperbolic alpha y. So as a result, now we have x and y. So it means that u of x and y, which is equal to x of x times y, is equal to a cosine alpha x plus b sine alpha x times c cosine hyperbolic alpha y plus d sine hyperbolic alpha y. So in this case, we could solve partial differential equation as well. Now the third case. So in the third case, we assume that lambda is a negative number. So I show it by minus alpha squared. Alpha squared is always positive. Minus alpha squared is negative. In this case, we have x double prime minus alpha squared x is equal to 0. As a result, x of x, it's equal to another constant. So let's say again I used a and b. So a cosine hyperbolic alpha x plus b sine hyperbolic alpha x, and we have y double prime plus alpha squared y is equal to 0. So it means that y of y is equal to c cosine alpha y plus d sine alpha y. So again, we could find x of x and y. Again, I say that these coefficients a, b, c, d, they are unknown coefficients, and they are different from what we found in case 2 and case 1. So in this case, u of x and y, which is equal to x times y. So it's equal to a cosine hyperbolic alpha x plus b sine hyperbolic alpha x times c cosine alpha y plus d sine alpha y. So we could find solution of partial differential equation when lambda is negative as well. But the question is that when when lambda is equal to 0, when it's equal to a positive number, and when it's equal to negative number, they all depend on the boundary conditions, and they depend on initial conditions. So I'm going to talk about it in the next lecture. So we could solve this given partial differential equation using separation of variables. So now we're going to talk about superposition principle. So based on this principle, if u1, u2, u3 up to uk, they are all solutions of homogeneous linear partial differential equation, then the linear combination of u1, u2, u3 up to uk, which is equal to c1 u1 plus c2 u2 plus so on ck uk, this one is solution of partial differential equation as well. So in this case, c1, c2 up to ck, they are all coefficients and they are all constant. So for example, for this equation, so second derivative of u with respect to x plus second derivative of u with respect to y equal to 0. We already solved it. So one solution is cosine x times e to the power of y minus e to the power of minus y. The other solution is equal to sine y e to the power of x plus e to the power of minus x. u1 and u2, they are both solutions of these partial differential equation. Based on superposition principle, we can say that u of x and y, which is combination of u1 and u2, so it's c1 u1 plus c2 u2. This equation or this function is a solution of given partial differential equation as well.